As we delve deeper into circles, we're going to be introduced to a lot of new vocabulary. So please take note of the diagram over on the left. Here are some new words alongside some old words. So in our last lesson, we were introduced to tangent lines, which touch a circle at exactly 1 point and only 1 point. Well, what happens if it didn't touch at 1 point and only 1 point? That would be called a secant line. Now, if a secant line didn't go as a line, it was only a line segment starting and ending at the edge of the circle, we would call it a chord. Now, you're familiar with the most famous type of chord, which is the diameter. Diameter has to go through the center, which is why we don't call it a chord, we give it its own special name. The last one is one that we're going to see a lot today, and that's an arc. An arc is tracing along the edge of the circle, but only for part of it. Now, when we start delving into arcs, we are going to have two different things to keep in mind. If I'm talking about the arc measure, I'm going to give you degrees, and this is going to be a measure between 0 and 360 degrees, usually not 0 or 360, but something in between. If I'm talking about the arc length, I'm talking about the outside of the circle, this arc that it forms on the edge of the circle. And that's going to be a distance. Now, the distance depends on how long your radius is. So, for instance, here I have a set of concentric circles. Concentric circles share a center, but they tend to have different radiuses. Here, the arc measure is the same, but the arc length is going to be very different because one of these is obviously a much bigger circle. So our first problem involves finding the arc length. Here I have the arc measure is 40 degrees, and we're trying to find S, which is this distance along the edge of the circle. Well, what we're going to do is we're going to use proportions. We're trying to figure out what portion of the circle does S represent. Well, 40 in relationship to 360 degrees tells us what portion of the circle is that arc. S is then compared to the circumference, which would be all the way around the outside of the circle. When we put this into a proportion, make sure that the small things stay together. So I've got 40 degrees on the top and I've got S on the top. Then we're going to plug in for the circumference 2 pi times the radius. So 2 pi times 10 makes 20 pi. Personally, I like to simplify my fractions before I start working with them so I don't end up with huge numbers. And 40 over 360, I can cross off the zeros on the end, and this reduces to 1/9. Then, finally, we'll cross multiply. 1 times 20 pi makes one side of my equation, and 9 times S makes my other side. Divide, and we get 20 pi over 9, which you can simplify if you want to, but leaving pi in an equation is perfectly acceptable as your answer. Our next problem requires a little creative thinking, and it involves what are called chords. And in this case, specifically, we're looking at congruent chords. Now, in order for two chords to be congruent, they have to be equidistant to the center. So this is our little image to help you kind of visualize what that means. It means that a point that is closest to the center is going to be exactly the same distance on both of these because they are exactly the same length. So we're going to use that in our problem over here on the right, where we have some extra information, but we're also missing some information. AB is equal to 8, DE is equal to 8, and CD is given as 5. We're asked to find this distance CF. Now, because AB and DE are given as 8, we know that they must be congruent. And we can work backwards that it forms those right angles, which thankfully they've already drawn into the diagram. Now, the tricky part comes with how on earth do I find CF when there's absolutely no information on that side? Well, we know that CF must be, by definition, congruent to CG. So if I can find CG using perhaps this little triangle here, then I can find CF. So the really tricky part is figuring out what is this other side of the triangle. And it took me a second to think about this, but they gave us information in the description that you can use here. So DE all the way across is 8. And because it's cutting it as close as it can to the center, this is actually the bisector. So it's a perpendicular bisector of that chord. So, short answer is we can take the length of DE and just cut it in half. So DG is 4. And now we have a very common right triangle. We know the hypotenuse, we know this is a right angle, we know one of the legs, and we're trying to find the other leg. You're using subtraction here, finally end with a square root, and with a little bit of logic, we know that CG is equal to CF, which would be important if we were doing this in a proof. So CF must be equal to 3. The last thing is a little vocabulary. Just like we started off with vocabulary, arcs can be put into their own little classes. If you have an arc that is less than 180 degrees, it can be called a minor arc. If it is more than 180 degrees, it can be called a major arc. Semicircles cover exactly 180 degrees. And because this is a little confusing, how would I name my arc might be a good question. I can't say BAC because it's not talking about the angle. So the minor arc here could be labeled BC, and we'll do like a big arc like that over the top. And then to show that this is a major arc and obviously not the same as the BC there, we're going to use this point D to name our major arc. So this is going to be BDC with a little arc symbol over the top. Same thing can be done for the semicircle EHG with the arc symbol over top.